And we are back, and we are about to do our P-Set4 solution video. So let's go ahead and get started. All right, so we have the following diffusion couple. We find the concentration profile here. Where does the interface move? Where are planes created? Okay, so we can see that 3 is diffused, or actually the green color is diffusing more into the purple than here. And so we know that in the C-frame, we need to have the flux of green in the C-frame plus the flux of purple in the C-frame plus the flux of vacancies in the C-frame must be equal to 0. So we know that green is going over here. Actually, I would switch pen colors, but so we have a lot of, basically, actually let's just draw it. That's going to be a large flux because we know flux from Fick's first law minus d grad C. So our amount of flux, looking that we're kind of, basically these are symmetric, they should be basically based on the diffusivity value. So the flux of green in the C-frame is here. Purple is not diffusing as much, smaller magnitude for purple, so we know that the flux of vacancies must also point in that direction. So what are we looking at here? We have lots of atoms flowing in on this side. And again, there's these extra half planes of atoms everywhere, right? So like missing, basically they can go here, filling in here. So atoms are filling up these planes, extra half planes are getting filled, whereas these extra half planes are leaving. So we are creating on this side, we are destroying on this side, vacancies are flowing on this to gobble these guys up. So we're going to expand here, we're going to effectively contract here, so this interface will move to the left, and that is always going to move in the direction of the flux. So that's essentially what's happening. Where will we have Kirkendall pores? So the pores will, and we also know the diffusivity of green is greater than diffusivity of purple. So perhaps this has greater solubility, perhaps it's smaller. We'll have to see those. Where will pores form? If we have large enough temperatures, long enough time, right there. Excellent. I want to model the diffusivity. I want to model the diffusivity of materials, write out the boundary conditions, and solve for the concentration profile as a function of time and space. So we know that we're going to look at Fick's second law, d grad squared c, which basically we can reduce this to if we're looking at a 1D problem, d squared c dx squared. This is our PDE. We want to use our ODE. So we want to use that eta is equal to square root of basically, eta is equal to x over square root of 4 dt, and then we're going to use that our d squared eta, d squared c, d squared c d eta squared plus 2 eta dc d eta equals 0. And let's actually double check 1 second that we have that correctly. There's always a minus sign that I occasionally get wrong. And it's something that, for the life of me, and partially because typically we're going to actually solve the PDE, but you'll get to experience that in another later class once we get into our really nice MEC 193 problems where we solve those. So we just want to make sure before we move on. But nope, I've got it right. And I just also want to check. Yep, we're good to go. So trust in yourself, Professor Steinle. So excellent. So we've got that. So I am going to invoke the semi-infinite solution. So I'm going to draw, I'll actually do right here. I'm going to treat this as, this is at x equals 0, this is x equals positive infinity, this is minus infinity. So if I want to, I need 2 boundary conditions. So for example, for green, I know that my concentration of green when eta is equal to infinity must be 0. My concentration of green when eta is equal to minus infinity will always be 1. And I could do the opposite for the purple. So those are my boundary conditions that I need to solve the PDE. The process was carried out, so excellent. And then we'd solve it. The process carried out at a temperature of 800 C for 10 hours. What is the highest diffusivity my material can exhibit before my assumption breaks down? So we know that L must be greater than 10 square root dt. So we are given that the length is, actually let's pull out Mathematica. Let's clear everything, quit the kernel. I am told that my length is equal to 0.75 meters. We know that the time is equal to 10 hours. 10 hours times 60 minutes times 60 seconds. So let's solve. L set equal to 10 times square root of d times t. And once Mathematica wakes up, we'll be able to do this. There we go. That's got to be my diffusivity. Fantastic. All right. I want to coat my green material with a 10 nanometer thick layer of manganese operating at 800 C. How long will this take? So I want to coat a material. So we're going to use our engineering approximation. X is equal to basically square root 40t. So I want to coat my material with the 10 nanometer. That's our X. Operating at 800 C. How long will this take? So we do have manganese. Oh, but we don't have 800 C. So how are we going to solve this? Well, we're going to actually have to calculate. We know that basically d is equal to d naught times exponential minus qa over kt. So we're going to have to get a little bit down and dirty to actually solve this problem. So we'll come back to this later once we solve for diffusivity, and actually we're going to solve these activation energies first for number 4. So let's calculate activation energies using these graphs here. So I'm going to just pick a constant dopant concentration, and I'm just going to kind of put it over here. Or actually, tell you what, let's mix it up a little bit. I am going to look at this right here. That's going to be my constant concentration, and I'm going to effectively see, I'm going to say that this is where we've doped it enough or sufficiently to get our layer. So that's going to be our value. And now I'm going to calculate my activation energy. So when it crosses the line, I know it's basically penetrated a depth of this X. So let's look at our manganese first, and then we can repeat the procedure for iron. So let's get started. I'm going to clear everything again. So if I look at that first picture, actually let's just do XFE. Let's just say that's approximately 750. XFE is equal to 750 times 10 to the minus 9. Let's look at, so we have our, basically the depth that penetrates for iron. So that's one of them. So let's do our expression as well. Let's pick another iron, basically. Let's go look at here, and we have that. And actually, so this iron that we picked, and I believe it's the small dash one. So we did the time one, TFE1, is equal to 15 minutes. So 15 times 60, because we want SI units, seconds. We're also told that it is at 1000 C. So TFE1 is equal to 1000 plus 273. And we're also, so that's all our first kind of data point there. So we can actually pick now our second crossover point here, and that looks to be iron at about, let's just say that our XFE2 is equal to 1250 times 10 to the minus 9, and those conditions are TFE2 is equal to 15 times 60, and our TFE2 is equal to 1050 plus 273. And we could do now the same thing for basically MN as well. So I'm going to do this, copy, and I'm just going to change MN. I'm going to copy this. This may be tedious, but this is how we're going to solve this problem. We're going to make sure that we know how to do it. All right, so now let's pick our MN kind of points here. I want to pick here, like, seems to be MN at like 2000. So I'm going to do 2000 here. What are my conditions? That's the dashed. So again, it's 15 minutes and this one's at 1050. And why not go over here to like about 2500? And then what's my time? Those are the small dashed. So that's 100 minutes. And that is 100 minutes at 1000. There we go. So I've got this, and I'm going to do EF1 is equal to, remember, so I need to solve for what? So we're given this, so I need to solve for diffusivity, and then I need to solve for the rest of my unknowns here. So let's first solve, solve that, for example, x Fe1 is equal to square root of 4 times d times t Fe1. So look at this here. So this is I'm going to call this my diff Fe1. I can do the same thing here for change 2 and 2. This is going to be my diff Fe2 equals that. I could do now mn1 t mn1. So I got this. So that's my diff mn1. And then I could just change this to 2, change this to 2. And this is my diff mn2 equal here. And now we're good to go as well. So now I can start set my equation. So I want my diff Fe1, and I'm going to set that equal to d naught times exponential minus, and actually let's define k is my Boltzmann's constant, 1.38 times 10 to the minus 23. That's the joules per Kelvin. And so now we can get minus QA divided by k times t Fe1. So that's my equation 1 for Fe. I'm going to do the same thing for Fe2, Fe2, Fe2. And now I can solve EF1, EF2, solve it for D naught, QA, and I want to get my real values. And we got it. So I can copy this now. I got my activation energy. I've got that. So I need to do M1, diff mn1, t, this is TDS, but it's important so that we can learn mn1 and diff mn2. There we go. Let's make sure this is 2. So we got this, EM1, EM2, and oops, let's see what we've got here. That's the problem. See, there we go. So we got our values. So I've got the activation energy. So boom, boom. So again, I wanted to coat my green material with a 10 nanometer thick layer at manganese operating at 800 C. So I'm going to give my full equation. So my diff Mn is equal to my D naught times exponential of minus that activation energy divided by K times T. And if I want my diff Mn at slash dot T goes to, that's 800 C, but I need to do 800 plus 273. We got it. So that's my diffusivity. So now I'm going to solve how long will it take for 10 nanometers, 10 times 10 to the minus 9, set equal to square root of 4 times diffusivity, which we have here, times T. And there we go. We got the time. We're good to go. Now let's move on to number 5. So let's go ahead and tackle number 5 now. And what I want to do is delete all this stuff. And let's kind of try to zoom in a little bit that we can read, but also so we can start to work and write. All right, so we have PCl. I want to dope it with MgCl2. PCl5, MgCl2. So potassium, or actually, excuse me, phosphorchloride. I mean, I'm not even phosphpentchloride. Again, I didn't take organic chemistry. So we can form anion, cation, Frankels, and then Schocke's. Activation for anion is 1. Frankel 2.2, Schottky is 0.1, so that's the dominant interaction. So for I'm going to break up my intrinsic, and we're going to do our steps. So let's write out the Schottky. So I'm working with PCl5, so null goes to vacancy in phosphorus. What's that charge? Plus 5 is 0, 1, 2, 3, 4, 5. So we've got that, plus vacancy of Cl is 1, but we have 5 of them. So second step, I'm going to write my K Schottky is equal to concentration of products. So it's going to be basically VP 1, 2, 3, 4, 5 times concentration of products over concentration of reactants. There's no concentration of reactants, so VCl to the 5th, and that equals exponential minus the G formation of Schottky over KT. So that's our reaction effectively here. So next step, electroneutrality statement. So I need to do VP 2, 3, 4, 5. Remember, put the charge out in front now, set it equal to the opposite charge, which is VCl here. Now plug in that equation. What are we interested in actually looking at? So we're looking at the diffusivity of P and the concentration of P vacancies. So that's what we want to kind of work with. So now let's do our fourth step, and let's plug that into this expression here, our electroneutrality, into our rate reaction statement, because we want to see how the concentration of phosphorus vacancies, how it varies as a function of temperature. So I'm just going to plug in, so VP 1, 2, 3, 4, 5, set that not equal to, excuse me. I'm just going to plug this in here, so this is going to be equal to 5 times VP 1, 2, 3, 4, 5 to the 5th power equals exponential minus G formation of Schottky over KT. So basically that's approximately VP 3, 4, 5, 1, 2, I mean, you know it's 5. 2, 3, 4, 5 to the 6th power is proportional to exponential minus G formation of Schottky over KT. If we take the natural, first of all, let's take the natural log. So then, actually, not first take the natural log, actually. Let's do the 1 over 6, put that there. Now we can do the natural log of this. This gets rid of this. And so we see that if we were to plot this, the natural log of concentrations of VP 1, 2, 3, 4, 5. So the natural log concentration over 1 over T, this is our 1 over T here. So the slope, and again, intrinsic, extrinsic, why? Higher temperatures, intrinsic dominates. So our slope value here is going to be minus G formation of Schottky over 6K. So that will be the slope there. What about for diffusivity? Well, we know diffusivity is related to what? So we actually derived that kind of together in class. So we had the hopping frequency, we had our R squared value here, and it's also going to be 2D. We had that basically correlation factor, and it's also going to be proportional to what? Basically the number of available sites, and since we're looking at diffusion of phosphorus atoms via vacancy mechanism, it's going to be proportional to this. So diffusivity, what about that hopping frequency? That's proportional to exponential minus G migration over KT. So if I'm looking at, and excuse me here, the natural log of diffusivity of phosphorus of 1 over T, I look at intrinsic, extrinsic, I'm going to have the same slope here because of this concentration dependence, but I'm also going to have this relationship here that's temperature dependent. And when I take the natural log, I'm basically going to have a slope that's minus G formation of Schottky over 6K minus GM over K because of this term right here. Excellent. Let's go ahead now, and I'm going to delete all of that. Let's delete that here. Let's do the extrinsic case, which is a little bit simpler. Extrinsic. So extrinsic, I'm doping it. My reaction is going to be MgCl2. Let me write that a little bit clearer. MgCl2 goes into my host PCl5. So I know I need vacancy phosphorus 1, 2, 3, 4, 5. Now I need to, let's say I put in plus Mg on an interstitial. So that's going to be 2. I'm going to do 2 of these. I'm going to do 5 of these. I'm going to put 5 here. I'm going to put 2 of these here. And then that's going to leave me with plus 10 Cl, Cl, X. Does that work? Looks good to me. So there we go. Second step, I'm going to do my, basically not my rate reaction. Again, here we're not temperature dependent because we're feeding it effectively in that reaction. So we need our electroneutrality statement. So Vp, 1, 2, 3, 4, 5. Again, put the 5 in front, and then 2 Mg, other side, interstitial. There's my reaction here. So how does this relationship vary with temperature? It doesn't. So that is just flat. And actually the value would just be the natural log of this. So there's going to be no temperature dependence here. But when we look at the extrinsic regime and we look at diffusivity, this will be flat. Here, no temperature dependence, but we still have this here. So I'm still going to have, a slope of G migration over K. That's it. So we're going to follow a very similar path for the next problem right now. Excuse me, I'm just, I'm in a very, I can't not catch my breath, but although, again, this Kroger-Vink always takes my breath away because it's so interesting. Anyways, so let's go ahead and do our next problem. Very similar procedure. So working with mystery material here, I want to dope it with this. So again, I'm going to have my intrinsic. Let's see what reaction is dominant. Anion 2, activation energy for cation is 1, Schottky here. So Schottky is going to be our dominant defect because there's the lowest activation energy. So let's go ahead and see how, and I'm looking at concentration of my alpha vacancies. So again, what I'm going to draw, ln of concentration of vacancies of alpha, and I can see that alpha is a plus 12. So I'm just going to do 12 plus, just to kind of make our lives to make our life a little bit easier. And I'm just going to do again of the 1 over T. And we could also do the same thing for the natural log of the diffusivity of alpha versus 1 over T. And then we have the intrinsic, and we have the intrinsic and extrinsic, as we've done before. So first step, I need my null reaction. Vacancy of alpha is going to be basically 12 plus, plus vacancy of oxygen. Again, that is technically, 12 minus, minus 12. Minus 12. I'm using this as a shorthand. It's not technically correct, Kroger-Vink, but that's a lot of dots to put, or actually dashes, primes. Now, K Schottky equals what? Concentration V alpha, 12 minus 12, times vacancy oxygen to the 6, exponential, let's zoom out a little bit, minus G formation of Schottky over KT. 3, electroneutrality. What do we need to do? 12, vacancy alpha minus 12, equals, we need 2, vacancy oxygen, charge out in front. Let's zoom out a little bit more. Let's plug this relationship back into here. So I'm going to skip a little, or not skip a step, but what we can see here when we plug in, I'm going to get an expression where my concentration of V alpha minus 12 is going to be to the 7th power, and that's going to be proportional to my exponential of minus G formation of Schottky over KT. This goes down to here. when I take the natural log, this gets canceled out. So my slope here is going to be minus g formation of Schottky over 7k. The diffusivity is going to be that same slope term here, but I'm also going to add on minus g and migration over k. Now for the extrinsic. The extrinsic case, let's zoom in a little bit. I'm doping it with Al2O3. So Al2O3 goes into alpha O6. I need to have a vacancy of alpha, which is minus 12. So I need to put in plus, because we don't want to change that. So I'm going to do an AL interstitial, and that's going to give me a plus 3. 1, 2, 3. And I'm going to put a 4 in front of that. I'm going to put a 2 in front of that. And then I'm going to be left with 6 oxygen, oxygen, X. That's my first step. My second step is the electroneutrality statement. So again, 12 vacancy of alpha, basically minus 12 here. And then set that equal to 3 a concentration ALI 1, 2, 3. Good to go. Charged out in front. So again, this is flat. What about here? Minus GM over K. And that is problem set 4 in a nutshell. This is a tough one, but again, I hope that you've done well, and I hope this makes sense, and then we'll be meeting again for P set 5 and then exam. So I'll see you in the next video. Thanks. Bye.